is a great transmission. Easily the smartest and most impressive I've ever been. All right, Space Dog, it's the night cycle. Let's go to bed. Okay, she's finally left. I'm entering the control room now. Great. Now don't get distracted by magic light cups. She knew we would be impressed with those. Don't give her the satisfaction. Now we've got a simple mission. Lay out a test for the creature so that we can determine if her species is intelligent enough to attempt communication with. We're going to test her with logic gates. It's foundational to computing, so it's imperative that we confirm this species has an understanding of them. If not, we'll need to keep a close eye on her and this other ship she keeps talking to make sure they don't get any closer to the planet. They could be dangerous. On it. Should I narrate everything I do out loud? Obviously, you should narrate everything you're doing out loud. Computers process information, which is basically just transforming inputs into outputs. Logic gates take input and produce an output according to sets of logical rules. While analog signals have an infinite number of values, digital signals are finite. They can only be 0 or 1. Digital devices represent these zeros and ones with 2 distinct voltage levels, which can be modified using logic gates. Microprocessors or microcontrollers like the Arduino use thousands or even millions of these gates. In the real world, logic gates are built primarily using diodes or transistors. A transistor acts like a switch or a gate for electronic signals. They open and close these gates multiple times a second and ensure that a circuit is on, represented by a 1 if current is flowing, or that it's off, represented by a 0 if it isn't. Most of them are made from MOSFETs, or metal oxide semiconductor field effect transistors. These are the most common type of transistors used today and are like a valve for electricity. They have one input connection called the gate, which acts like a switch to control the 2 outputs. There are 7 basic gates that can be combined to make much more complex logical elements. A basic gate is just a component with 1 or more inputs and 1 output, all digital. The gate uses Boolean algebra to set an output to either 0 or 1 depending on the input signal. Truth tables are used to visually represent the output logic based on the input values. Inputs are labeled A and B, and outputs are labeled Y. The NOT gate is the simplest and only has 1 input. It's sometimes called an inverter because it changes zeros to ones and ones to zeros. The AND gate outputs zeros unless all values are ones. This gate screens data and can either enable or inhibit the flow of data, so practical uses for these are data transmission or components like a push button. The OR gate outputs a 1 when either input is a 1. A practical use of OR gates is that they can act as fail-safes for either shutting down or activating machinery to protect it from damage. They can take in sensor input and correct any unwanted variations in their output. They're good for circuits where there's more than one power source available to perform a similar action. The remaining gates are variations of these 3 basic gates. The exclusive OR gate outputs a 1 when only one of the inputs is 1. The NAND gate is an AND gate with an inverted output. The output is 1 unless all of the inputs are 1. NAND gates are really common because you can create any of the other basic gates from a combination of NAND gates. Similarly, the NOR gate is an OR gate with an inverted output. It outputs a 1 if both inputs are 0. The exclusive NOR gate is an inverted exclusive OR gate. It outputs a 1 if all inputs are the same, either 1s or 0s. These seemingly simple gates make up the foundation of what we're able to do with computers and electronics. First, we declare Boolean variables, so true or false, for both of the push buttons and the output of each logic gate. Then we set the pins for the buttons and the LEDs. In void setup, we're starting the serial monitor and setting the buttons as inputs and the LEDs as outputs. In void loop, we're first just reading whether each button is pressed or not. Then we're stating how each output is going to work based on the 7 logic gates. Then we print out the button and the logic gate state to the serial monitor and then turn on the LEDs based on whatever the push button state is. So here's what should happen for each of these individually. Exclusive NOR lights up when both buttons are pressed or both are not pressed. Exclusive OR lights up if only one button is pressed. NOR lights up when neither button is pressed. OR lights up when either button is pressed. NAND lights up when neither or only one of the buttons is pressed. AND lights up when both buttons are pressed, and NOT lights up when no button is pressed. When we don't have any buttons pressed, exclusive NOR, NAND, and NOT all light up. Pressing both buttons lights up exclusive NOR, OR, and AND. And pressing one button lights up exclusive OR, and NAND. I think I hear her coming back. Hurry, wrap it up and get back to the ship. I almost forgot about the nightly systems check. Okay. What is this garbage? Test your understanding of logic gates. Determine which LED will light up based on various push button states. No thank you, that sounds like effort.